Alright, we're going to try to attack this population problem of small rodents here. I outlined a solution for you. Um, so you always start off any population problem, you can start off by with this model here. This is the general population model. Um, we were told in the problem that beta, the birth rate, was 0.001p. So I take that value of beta, I plug it in there. That's the first step. And then we're also given some information at we're given two pieces of information. At time t equals 0, so that's like today, there are 100 rodents, so the population's 100, and also their population is growing at a rate of 8 rodents per month. That's a rate of change, so that's exactly dp dt. So dp dt at that time is 8 rodents per month, and yeah, that lets us know that t is being measured in months here. So what we can do is we can plug those values in, right? Those are the values when t is 0. So we'd have 8 equals 0.001 times 100 minus delta times 100. Okay. And yeah, see, we can use that to solve for delta. We'd have to divide both sides by 100. So we'd have 0.08 equals, now 0.001 times 100, that'd be 0.1. Okay. So that means delta would be 0.1 minus 0.08, which is 0.02. Okay, so that's the value of delta. So that means, and delta is constant, so that means that, that's not only the delta for when t is 0, that's always the value of delta. So we can go ahead and plug that in to our general formula here. And so there's our differential equation. Okay. I'm going to do a couple things to that. First thing I'm going to do is this p right here, I'm going to put it out front. And then I'm also going to, from what's in the parentheses, I'm going to factor out the 0.001. Okay, so that would be, that would leave me with p in the parentheses, and then it would leave me with 0.02 divided by 0.001, which is 20. Right, that's what would happen to the 0.02 if I factored out a 0.001. If there's any doubt about that, go ahead and take the 0.001, distribute it back into the parentheses, and just see that it's equal to what we started with. Okay, so we are going to solve this by separating variables. Whoops. The denominator there should have been dt. So let's see, we're going to get all the p's on one side, all the t's on the other side. Okay, we want to do partial fractions. On the left side there. Okay. To figure out what goes above the p, you cover up the p, you plug in p equals 0. That'd give you 1 over negative 20. So negative 1 over 20. To figure out what goes above this term, you cover up that term, you plug in p equals 20. You'd have positive 1 over 20. So that's how the partial fraction decomposition works. So let's go ahead and multiply both sides by 20 to get rid of those fractions. So if I do 0.001 times 20, that would be 0.02. And then I'm going to reverse the order here just because this one is negative. So I've got, I'd have 1 over p minus 20 minus 1 over p, all dp. So now I can integrate. Okay. And yeah, the main reason, why do you, why up here, why do you factor out the 0.001? It's because then you don't have anything in front of the p, in front of this p right here. Okay, and you don't want anything in front of that p because when it gets down to this point, if you don't have any coefficient in front of the p, this becomes a much simpler integral. Okay, this is just going to be the natural log of p minus 20, and then minus the natural log of p that would be equal to 0.02t plus a constant. Okay, yeah, see, if there was a coefficient in front of the p, that would lead to some kind of fraction in front of the natural log here, which you don't really want. Okay, and another thing here, technically there are absolute values, but keep in mind that the initial population was 100. That's bigger than 20, so p is bigger than 20, so I don't really have to worry about absolute values here. P minus 20 is positive. Okay, and so I can get rid of the absolute values. I can also rewrite, the difference of natural logs can be rewritten as the log of the quotient. So that means that p minus 20 over p would be e to the right side, which is the same as e to the c times e to the 0.02t. Okay, let's go ahead and use our initial condition, right? The initial condition was that p of 0 was 200. It wasn't 200, it was 100. That was told us in the problem. So that's nice because that means that when I plug in 0 for t, I get 100 for p. And yeah, the nice thing about plugging in 0 for t is that e to the 0 is 1, so that tells me that's going to allow me to figure out what that constant e to the c is. E to the c is 80 over 100, which is 0.8. Okay, so that e, that's the value of that constant there, so I can plug that in. So actually what we have p minus 20 over p equals 0.8 times e to the 0.02t. Okay. Now I could go ahead and get p by itself algebraically, but I don't really need to here because the problem was actually asking us to find a t so that p of t was 200. So I don't really want p by itself. I actually want t by itself. So let me go ahead and plug in. I can plug in 200 for p now. And really what I want to do, I want to solve that for t. Okay. Let's see, left hand side would be 180 over 200. That's 0.9. So 0.9 equals 0.8 e to the 0.02t. Okay. If I divide both sides by 0.8, I'd have 1.125 equals e to the 0.02t. So the natural log of 1.125 would be 0.02t. And so the natural log of, I'd have to divide by 0.02 to get t by itself. So we'd have the natural log of 1.125 divided by 0.02. I get that to be about 5.9, which I guess I'll just round that to 6. I'll say 6. And keep in mind, t was measured in months, so it's approximately 6 months.